Well, it's my very great pleasure and privilege to introduce the next speaker in this foundation series, Nancy Reid. I don't think she actually needs much of an introduction, but I'd just like to say a few words about her and my association with her, which has gone over a fair time. What isn't quite obvious, I guess, is that I was her master's student supervisor when she came to the University of British Columbia Math Department. And she not only survived that difficult period working with me, but in addition to that, she did some pretty foundational work herself at that time on the proportional hazards model, which is at that point pretty new, and it was actually adopted by some cardiovascular surgeons for deciding on treatments and for disease. So anyway, then she went to Stanford, worked with the late Rupert Miller on the same subject, and then did a postdoc following that in the UK. It turned out we had a position in the Department of Math to which she applied, and she was something like 300 or 400 applicants because the mathematicians were pouring in at that time, and she was picked out of that huge crowd, which was an enormous pleasure. And so one of her very important early contributions, in my view, was her contributions to the establishment of our new Department of Statistics in the University of British Columbia. And here she was, I mean, just barely out of a PhD program, doing a lot of stuff in the development of the department. So I've always appreciated that big contribution she made. And of course, the rest, as you might say, is history. She's gone on to an amazing career and has been so many awards that it would be impossible to even begin to try and summarize them all. But I would just mention that she did win the Copps Medal as one of her early achievements, and that was for outstanding contributions to the profession of statistics. So it was already recognizing both her work as well as her other contributions she was making at that time. That was considered at that time in the material that was circulated about the Copps that this was the Nobel Prize of Statistics. So there you go. Anyway, since then, all sorts of awards, and I'll just mention a couple. One being the fellowship in the Royal Society of the United Kingdom, and also a fellow in the Royal Society of Canada. And those are major honors. But more recently, she was made an officer in the Order of Canada, which is really a great achievement. Typically, people are first appointed as members of the order, and then they get promoted to officer and so on. But she was appointed as an officer. So. And in the citation, it said her research is aimed at finding more accurate and efficient methods to deduce and conclude facts from complex data sets, ultimately helping scientists find specific solutions to specific problems. So in today's lecture, perhaps she'll reveal some of the secrets that enabled her to do these things. And so, without any further ado, I'm going to invite Nancy to give us her lecture. Thank you.
Well, thank you very much, Jim. I owe Jim a lot more than thanks for the introduction today. He didn't touch on all the guidance that he provided me over the years. He also was in the audience for my first talk, and I hope my absolute worst talk. I haven't worsened it yet. It was just a little seminar in our department. I don't know if you remember, Jim, but I was so nervous I finished a 40-minute talk in 20 minutes. And I stopped and asked for questions and saw just blank faces staring at me like, what just happened? So I've learned to slow down a little bit. This is the end of the day, and we've had a lot of really amazing, strong technical work presented in the special sessions. So this foundational lecture, although it's on foundations, is meant to be relaxing and not quite so technical. The background is the series of workshops, of which I've attended several, that were, I think, probably Xiaoli Meng was the instigator, but Menge Xi and others have picked it up and carried it on over the years. And they're called the BFF meetings for Bayes, Frequentist and Fiducial, and also for Best Friends Forever. And we had the 7th conference in 2022, just a few weeks ago at Toronto. Here's another BFF from a poster from a pub in England. It says, "Beer, food, and friends." But Menge and Jim Berger and Xiaoli and I are working on a handbook, a collection of papers reflecting some of the developments in the series of BFF meetings. And I've stolen the cover from Grace Yee's book. I hope she forgives me, and Paul's handbook, because our handbook isn't ready. It was promised, of course, some time ago, and it's late. But we're academics. We know what that's like. So I wanted to. I wrote an introductory chapter for this book, and I wanted to give you a bit of an overview from that point of view. So the papers in the handbook are also kind of overviews themselves, so this is like a meta overview. But I'm going to start with an example, and it's a pretty simple one, but it got me thinking a lot. And you may well have heard of it. It's a few years old now. This was a randomized clinical trial to compare 2 treatments for septic shock. And the estimated hazard ratio, they used a Cox proportional hazards model. The estimated ratio was 0.75, and the 95% confidence interval includes 1, which means that the new treatment is not significantly different from the old treatment at a level of p equal 0.05. And the two-sided p-value for the test, the corresponding test, is 0.06. But there was a fairly substantial reduction in the percentage of people who died from 43 to 35, which was considered clinically quite meaningful, but it didn't quite make the cutoff. And so in the discussion, the authors said this new strategy did not result in a significantly lower 28-day mortality when compared with the old strategy. But in the abstract, that got a little bit simplified, and it said instead of did not result in a significantly lower, it said it did not reduce all-cause 28-day mortality, which is a slight change, but we understand that the meaning of those sentences are different, but the world probably doesn't. So the fact that our interpretations have to turn on such careful wording is a little bit worrisome, I suppose. And I'm indebted to David Spiegelhalter for tweeting about this. He said it's absolutely an example where p less than 0.05 is harming us, because here's a new strategy that has a substantial risk reduction, clinically meaningful, and yet the headline that people remember is it didn't work. So I can give just slightly more detail, but not exactly because I don't have the data. So what I've done here is just made a 2x2 table of the numbers who died before 28 days were up, and the numbers who lived and under the new and the old treatment. And I did a slightly modified likelihood ratio test. As I said, I couldn't adjust for the covariates, so the two-sided p-value from this simple little table is 0.07, slightly larger than 0.06. And what I've drawn here instead is a p-value function, which is, it gives you the p-value for every possible value of the log odds ratio. So it just presents in a kind of summary form all possible p-values in some sense as a function of the parameter of interest. And one reason for doing that is to kind of summarize the data in a way that's maybe a little bit different, but I was going to say a little bit more informative, but much more informative. And of course, you can easily construct the 95% confidence interval from these p-values, because you find out where the p-value function crosses 0.975 and 0.025, and that determines the 95% confidence interval. And you can see that it just crosses 0. But the 90% confidence interval is all the way to the left of 0, and the 99 is, crosses 0 more. But I put an arrow into 0 because I think there's some psychological effect of seeing this picture that makes you feel that, well, yeah, it's true that 0 is between the two blue dashed lines, so it's in the 95% confidence interval. It's awfully close to the edge, and somehow the fact that it is awfully close to the edge should be telling us something. And now, of course, if this was a Bayes posterior, it would be telling us probabilities, and I'll get to that. But from a strictly non-Bayesian point of view, there's a sense in which there's a kind of something that looks a bit like a survivor function, and could we interpret that as a kind of probability? So when I say distributions for parameters, that was the title of the talk. That's what I mean. I mean kind of something that looks distribution-like that we can ascribe to a parameter. And a lot of the work that's been done in the BFF setting is different ways to develop these distributions for parameters. So that's what I'm trying to give an overview of. Okay, so what I've just showed you is something that goes back all the way to Cox, 1958. This is his famous two measuring example paper, but there's a lot more in that paper than just the two measuring instruments example. It's quite a remarkable paper, and it's worth another look. And I highlighted, you probably can't see it, but I'll read it. I highlighted these two things because this is another aspect of statistics unrelated to distributions of parameters, but maybe more closely related to best friends forever. He says it consists of some general comments, few of them new, about statistical inference. And then later he says parts of the paper are controversial. These are not put forward in any dogmatic spirit. And you kind of, even in the abstract or the introduction, you get a sense of someone who's very measured and very open to ideas and not fighting for his own side of things, which was kind of the tradition maybe into the early 50s. And I think that it harmed our profession a lot that people were arguing so in such a almost childish manner about these philosophical issues. And David stands as, I think, a stellar example of the turn away from that. So in the confidence interval section of his paper, he just notes what I just showed you in pictures, that the method of confidence intervals usually gives you one interval, but he said in simple cases there seems no reason why we shouldn't work with a distribution. A confidence distribution for the unknown parameter could be defined directly or introduced in the terms of the set of all confidence intervals, which is how I showed it. And Brad Efron wrote a paper about this in 93 where he followed up on this idea, and he said something else about this type of confidence distribution. He said it assigns probability, for example, 0.05 to theta being between 2 points in the distribution if we interpret it as a probability. And he says, of course, this is logically incorrect, but it has powerful intuitive appeal. And I tried to illustrate that intuitive appeal with the green arrow near the edge of the curve. And he mentioned that with no nuisance parameters, this is exactly Fischer's fiducial distribution. So now I'll look at, for a moment, at Fischer's fiducial distribution, which has seemed to cause a great deal of misunderstanding over the years, but I don't think it's really as hard as all that. But it has a very weird-looking expression. This is from Fischer's paper on inverse probability, and he calls this expression the fiducial distribution of theta for a given statistic y. So the idea is it's a density. It has a d theta on the end, so it's a probability density measure for theta, but it's not a real probability measure. It's a fiducial probability measure. And so what on earth does fiducial mean? Well, it's very hard to sort out from what he wrote, but I'll try to give a bit more flavor for it. This is maybe one of Fischer's milder statements. I've left out the harsh bit that preceded it, but it's not to be lightly supposed that men of the mental caliber of Laplace and Gauss could fall into error on a question of prime theoretical importance without an uncommonly good reason. That's Fischer's long-winded way of saying it's kind of hard to see how to get a distribution without putting a prior on things, which I'm sure you're all thinking now, why don't you just put a prior on everything and the talk could be over and we could go out and eat some more of that nice food. So Fischer was criticizing Laplace and Gauss for taking a Bayesian point of view, but allowing that it's kind of hard to see what else to do until he came along with this rather mysterious construction. So I'll try to explain it as I understand it, and it might help a little, but I'll do it in the context of a very, very simple setting where we have one observation from a location model, and we know the density, we just don't know the location of the density. And we could write this as what's now called a generating model. That is, we got y by adding some error to a fixed value of theta. That's all pretty straightforward. And the idea is that once we've observed y, then we can write theta is equal to that observed y minus the error. And so somehow we're now going to take that equation and say that the variation in E, which we know its distribution, induces variation in theta. The probabilities for E generate probabilities for theta. I think it's sort of clear there's some philosophical arguments in the literature about what it actually means to say we've observed y and whether the same probability space is still relevant and so on, but putting those aside and just intuitively, we can kind of see that if E changes, theta is going to change if we keep y fixed. And that's really what Fischer did with that expression that I just put up. I'm going to put it up again here. But he did it in a way that wasn't completely clear in what he wrote. He essentially said, but he didn't quite say it like this, fix a percentile point of the distribution for y, consider that as a given, and then that creates a kind of relationship between y and theta. And on differential terms, we could differentiate that equation with respect to both y and theta. And that has to be equal to 0 because we fixed the percentile point. So in that sense, I know I've written df here to follow Fischer, but in that sense, dy is equal to minus d theta, f of y d theta. So it's a kind of converting this kind of fixed percentile to a way that y impacts theta and vice versa. So once we observe y, then we know something more about the distribution of theta. I find it easier actually to go back to the confidence and think of inverting it more directly. So here's a terrible picture, a sketch of we fixed y at our observed value, and we've decided on a quantile, a percentile. I called it alpha here instead of p because it's so much more usual. So this is the density of y, but the density of y depends on theta. So I've picked a particular value of theta that makes sure that we have exactly alpha to the right of the observed point. And if I picked a different value of theta, then I'd have a different value of alpha, or vice versa. I could pick alpha, decide that I wanted alpha prime to the right of the data point, and I'd have to figure out which theta value would actually make that happen, and I could keep doing that. So I'm mapping all these different alphas into values for theta, and when I'm finished, I'd have something like a confidence distribution, the inverse map that takes theta back to alpha. So I have a map from alpha to theta, and I could invert that and make it a map from theta to alpha. That's how Efron explained it in his paper. Okay, so I have talked about 3 different distributions for parameters. One was all the p-values, one was a confidence distribution, and one was a fiducial density. And they're actually pretty much all the same for easy one-parameter problems and one-parameter data. But they're not real probability distributions in the sense that they don't obey the rules of probability calculus. So if we had several of these, we couldn't combine them in the way that we're used to combining probabilities. And that's a particular problem when we want to go beyond this toy setting with just an observation and a parameter, because we want to deal with, of course, lots of parameters and very complex data. And there's not really a very direct way to adapt these to multi-parameter models. And that's why it's still being discussed in the BFF 1 through 7, that there still is something to discuss. So I'm going to try to convey some of the ideas behind that. Now, a Bayesian posterior, of course, is, as I mentioned, much simpler in certain ways. We introduce a probability function on the parameter space, and then we just use conditional probability to get the posterior after we've observed the data, and that extends very directly. We can do any, the data could be quite complicated. I've imagined here that it's a vector of size n, but it could be a network or a gene expression array or so on. And theta could be a fairly complicated parameter. It could be the weights in a neural network and so on, but conceptually everything is still the same. Computationally it's hard, but conceptually everything is still pretty straightforward. And all the probabilities that we want to compute, the probability of theta in any subset, is computed from the posterior distribution by integrating over that set. And this is a cover of the, Steve Stigler pointed this out a few years ago. The original title for Bayes' paper was a method of calculating the exact probability of all conclusions founded on induction, of all conclusions founded on induction. The published title was much milder. It was like an essay on the doctrine of chances, something like that, right? Towards, it was much toned down from this, but this computing all probabilities, I think, of the attraction of the Bayesian approach. So, yeah. Now, so I'll come back to this simple 2x2 table because David Spiegelhalter had said that, this is a travesty, P is 0.06, and people are making this conclusion. The authors of the original paper actually went back and did a Bayesian analysis of it in a later paper. So in their original analysis, they looked at 28-day mortality. They used proportional hazards model, and they adjusted for 5 covariates. And the results are, as I mentioned earlier. The Bayesian reanalysis was changed a few things, which I think makes it a little harder to compare directly. The reanalysis was based on logistic regression, so it's a little closer to this 2x2 table. But then they also have adjustments for confounding. And they focused on the posterior probability that the log odds ratio was smaller than 0, which is essentially the same as focusing on the probability that the hazard ratio, or the odds ratio in this case, is less than 1. They did a bit more. They added a random effect for center because this trial was carried out at several centers. As I mentioned, they changed from proportional hazards regression to logistic regression. And now they have since they have 5 covariates, they now need priors not only for the log odds ratio, but also for the 5 covariates. And it's pretty unclear what they did for all that. The priors for the odds ratio are carefully set out. They had 4 different normal priors on the log scale for the odds ratio. And the posterior probability for the odds ratio being less than 1 ranged from 0.94 to 0.99, and that was, roughly speaking, from there. They only had 4 priors, but one was what they called pessimistic, one was optimistic, and 2 were kind of somewhere in between. And the pictures are here, so they had 4 different priors. The probability that they're talking about is this tiny probability here to the right of 1, or, well, the large probability to the left of 1. So 0.99, I think this is 0.98. This is 0.94, so not quite as convincing. And this is, I think, also 0.98, although I stand to be corrected. I don't remember exactly what it's high. It's well over 95%. This is called a null prior. It's a flat prior on the odds ratio. It's actually a normal prior with a variance 10,000. So it's not quite not a prior, but they called it a null prior. There's another Bayesian analysis by Van Zwet and Steven Sen and a colleague, whose name I can't remember. They used an empirical prior, quite a different one, they looked at all the randomized controlled trials in the Cochrane collaboration of a certain type, and they developed a prior from what usually happens in published randomized controlled trials. They got a smaller posterior probability for the odds ratio being less than 1. It was about 0.91. However you slice it, it seems like somehow we're slowly convincing ourselves that this treatment is worth looking into, right? It's not, we shouldn't take at face value the original conclusion that the new treatment didn't have a material influence on the probability of survival. Okay, so to come back to this kind of focus on distributions, I think as I'm preaching to the choir here, the inference is kind of intuitive. It combines easily with decision theory, and it gets away from point estimation and arbitrary cutoffs. So all those things are to the good. And as was noted in the discussion of confidence distributions, it's tempting to conclude that the parameter is more likely in the middle of the interval than near the edges. Or as I mentioned, it sort of feels like it's assigning a probability. The confidence distribution is assigning a probability to different intervals. So in that sense, the inference statements are become kind of probability statements about unknowns, but in fact they're not really, and I mentioned this before, but I wanted to emphasize it again, they seem to be probability statements, but it's a bit more subtle than that. And unfortunately, we have to think then a little bit more about what the probability means. So in a Bayesian analysis, we have probability in and probability out. It's kind of clear cut. And then the discussion is, A, where does the probability in come from? And B, how do we compute? So it's a little bit easier. But the way most of us learn about probability initially is as a more empirical concept that describes physical haphazard variability. And most of these ideas are in David Cox's book in 2006, his Principles of Inference. But we wrote a paper on some of these ideas in the International Statistical Review. And we described this with empirical, or sometimes called aleatory probability, which are the probabilities we teach in second year, the long-run frequency, or the probability of a large population of like units having some property in its full distribution. But a Bayesian posterior is a probability that's epistemic. It's a probability that describes the uncertainty of our knowledge. And it could either be our personal uncertainty, or our personal degree of belief following Savage and Ramsey and DeFinetti, or it could be kind of following Jeffries as some impersonal, rational degree of belief that we could all agree was appropriate. And so none of this is in the slightest new. I just managed to avoid thinking about it until about 2015, because it's kind of hurts your head, although it hurts my head anyway. But when we say with a confidence distribution, we say, oh, here's a distribution function for a parameter. And so if we're to say the probability of the parameters between one number and another number, what does that probability mean if it's a confidence distribution? Is it supposed to be empirical? Is it supposed to be measure our uncertainty of belief? I don't think that even the people developing these distributions have quite agreed on what they are yet. Okay, so finally I'm coming to the handbook. These are, I've talked about posterior distributions. So I've got one column is kind of old and goes back a long, long way, and the right-hand column is what's in some of the things in the handbook. So there's a Bayesian part, there's a fiducial part, there's the confidence distribution that I've been talking about. There's significance functions that Anthony Davison and I wrote a chapter about, which builds on a combination of structural probability and the significance function that I opened with. And then there's more. There's things on the kind of fuzzy sets and belief functions, upper and lower probabilities, inferential models and so on. The point of this slide is just to show that in a lot of work that's being done today, that's pretty theoretical and not quite working its way into big applications. All the old ideas are kind of coming back in a new form, and I think that's always kind of interesting, in my opinion. And of course, underlying all of this is the new emphasis that's quite modern on high-dimensional inference, model selection, and computation. Okay, so now what I'll do is I'll just try to cover some of these topics on the right-hand side at a very high-level view: objective Bayes, generalized fiducial, and confidence distributions. And if there's time, but there might not be, I'll try to do approximate significance functions. Objective Bayes would be probably the most familiar to everyone in the audience. There's many, many, many proposals for priors that are meant to be not very influential in some way. Reference priors are perhaps the best known. Default priors, matching priors, vague priors. Jeffrey's prior is a popular choice that's based on expected information. So what's the interpretation then on the posterior distribution? Should that be empirical or epistemic? And what we argued in 2015 was that if we're going to use some kind of, let's call it objective for lack of a better word, prior, then the probabilities that come out are not really meaningful probabilities in the sense of describing our uncertainty, because we've put in something that we hope is not very influential. So what Cox argued forcefully is that you could think of this Bayesian argument as you would think of a measuring device, and you would see how good it is by seeing how well it does in practice. And in practice is what he described as a scheme of repetition, where we use empirical frequencies to actually check that our posterior distribution has the properties that we think it has. So we try to make sure that this uncertainty probability that we'd like to ascribe to it actually has an empirical basis in sampling. In Cox's words, it's unacceptable if such a procedure that yields high probability regions in some non-frequency sense, by which he means epistemic, or our uncertainty about it, are poorly calibrated. That is, they don't actually correspond to high probability regions in a frequentist sense. Because if we use these procedures repeatedly, we get misleading conclusions. There's a wonderful series of papers in the volume 1 of Bayesian analysis on this topic that's still worth another look, because there's both points of view expressed forcefully and eloquently. Okay, so I said this already. There's lots and lots of vague priors, but many versions of these non-informative or non-influential priors are not correctly calibrated. And it requires, unfortunately, checking in each example. And that's because the calibrated versions essentially must be targeted on the parameter of interest. And if they're not targeted on the parameter of interest, then they won't be calibrated. Or it's impossible to find a single prior that works for all possible parameters. Maybe I've said this. In very special cases, only in very special cases, can calibration be achieved for more than one parameter in the model from the same prior. So in that sense, we're losing the simplicity of a Bayesian approach, because we'd like to put prior in, data, posterior out, and then worry about what summaries to look at. Oh, now I'm interested in theta 1. Now I'm interested in theta 2 over theta 3. Just marginalize, and use Bayes' claim that you can compute the probabilities of all events based on induction. And you can't really do that and still be calibrated in the frequentist sense. And for that reason, then, the simplicity of a fully Bayesian approach is lost. Gelman pointed this out in a paper on weakly informative priors. So what I mean by simplicity is that, just what I said in words, if we want the posterior distribution for a particular parameter, then integrate the simplest way, the standard way to get it is to marginalize the posterior. Before I had a set A here, now I have a particular choice of A. We can't really be sure that this will work for any psi we choose if we just pick a single prior, because the prior can have unexpected influence on the posterior, even when it's seemingly non-informative. So this also, none of this is new. This all goes back to Stein in 1959. He pointed out that if you took a series of normal observations with different means and put flat priors on all the means, then the posterior is easy to work out. It's a normal, multivariate normal, centered at the data. This probably seems like way too simple, but it's actually reappeared in recent developments of Bayesian inference, especially in non-parametric and high-dimensional settings as the sequence model. In this model, I'm imagining that we'll see in a minute, but we might be thinking of all the thetas as non-zero, and we've put flat priors on all of them. In the sequence model, we're expecting that lots of the thetas are zero, and only some of them are influential. But in Stein's example, it's simpler to work with something a bit more direct. So just repeated the model here. The posterior distribution is well calibrated. The marginal posterior distribution is not. The posterior distribution of any linear combination of the means is also well calibrated, but the marginal posterior of the length of the vector, for example, if we decided we were interested in the length, then the marginal posterior distribution is quite misleading. And it's easy to work out almost exactly. The discrepancy is a function of the number of different means and the variance of each yi. If you want to think of the sequence model where n is 1 and k is n, then the discrepancy would be a function of n over psi, essentially. And it's the reason it's easy to work out is because the p-value or the significance function, the obvious frequentist answer is based on a non-central chi-squared distribution where the parameter is part of the non-centrality, whereas the Bayesian survivor function based on that flat prior is a non-central chi-squared distribution where the non-centrality parameter is a function of the data, and those two functions go in opposite directions from the middle, which is what I've shown here. The three red lines up to the right are Bayesian posterior values, and the three blue lines down to the left are frequentist significance functions, or p-value functions, and they're diverging as k gets larger. So as you go out from the center two lines, k is getting larger. So the more different means you have, the worse they are. So you would say this, I would say this is the right answer, and this is starting to become badly wrong if you have several means. That's the easiest example where we can work it out so directly. In the complicated and important and more interesting data sets that we're all working with today, we can't always check all these things so easily, but the fact that it fails so badly here makes me nervous, at least. So it's one example of things going wrong when you think they might not. Just a mention in passing, the global local shrinkage priors like the horseshoe prior and the slab, the spike and slab lasso prior and so on, they do shrink the posterior back in the right direction, and so do the reference priors. It's just that you need to think about it. It's not, and when you're working with a very complicated application, it's hard to think about it because you've had a lot of work to do just in the data itself. Okay, so calibrated posterior distributions just have to be targeted. I've mentioned two types of objective posteriors based on matching priors or reference priors, and they both are expressly targeted on the parameter of interest, but most are not. If you run through the Annals of Applied Statistics and look for the Bayesian papers, you won't find the priors particularly targeted on the parameters of interest. And to come back to this 2x2 table, or the more complicated version with covariates, the Andromeda Trial, they put normal priors on the log odds ratio. Possibly okay, I don't know. But on the regression coefficients, they didn't really say what they did. And they just said we used vague priors on the regression coefficients. It might not matter. These are the regression coefficients for all the covariates. It might not matter. There's only 5 of them, and maybe they're kind of sufficiently independent of the odds ratio, the treatment covariate, that it's not going to make a huge difference. But it hasn't been checked, right? We don't have really any way of knowing. And the closest I got to figuring out what they did was they did put their R code online, and the model fit is really it's embedded in a program that's available online for Bayesian logistic regression. And they haven't specified, they specify very clearly in the code the priors for the odds ratio, but they didn't mention anything in the code about the priors for the regression coefficients. So I'm assuming that there's a default built into the program, and they've just assumed that default built into the program should be okay. And maybe it is, but it hasn't been checked. It hasn't been checked. Okay, so I actually said I used a likelihood ratio test for this, but I didn't quite. I actually did target the odds ratio by using a conditional distribution, given the marginal totals, which in a 2x2 table is pretty straightforward. And there's an easy way to target the sum of the squared means in the Stein example. You just take the sum of the squared data and use that as your estimate or your statistic, and don't worry about the full posterior or the full distribution. That is, we can easily boil things down to one parameter problem. So we don't have to marginalize our Bayes posterior. We don't have to worry about nuisance parameters in our frequentist approaches. There's straightforward ways to find a variable that measures the parameter that we're interested in. But those are really easy examples, and that's not always the case that it's that straightforward. And actually, Fischer said this way back in 1930. He said, well, yeah, I know I've only done it for one variable and one parameter, but we can always find a variable that measures the parameter we want, and then everything's fine. So an awful lot of the more recent work is trying to, I think, zero in on that in one way or another. Okay, Jim, I don't remember exactly when I started, and I know we have a lot of fun tonight, so I shouldn't go on too long. So I'm going to, what do I have next? I'm going to skip the confidence distributions with apologies to Mingei Shi and Niels Hjort, and they've all done a lot of interesting work on this. I wanted to show you, as best I can, and the approach that Jan Hanek calls generalized fiducial, because I think it's kind of intriguing. I've got only 2 slides on this, and it's I've heard like 10 talks by Jan Hanek, and I still don't quite get it, so it's a little bit bold to put it in 2 slides, but I think it's kind of an interesting approach that's maybe not been fully explored. It's very closely related to confidence distributions, I must say. Okay, so location model we've already seen. Now I have a data generating equation that has n observations at least. In this location model, it's easy to see that as soon as we observe the whole sample, we know more about the error than just that it's equal to theta minus y, because we know all the differences, or we know what EI minus E bar is because we know what the YI minus Y bar is, and theta isn't involved in that. So we can boil it down to a one-dimensional problem right away. Okay, that's just the location model. In general, the generalized fiducial starts with what Jan calls a data generating equation, which takes a known distribution and a parameter and produces some variable, just like the location model. And then once we have the data, we find the inverse. Jan describes it slightly differently. That is, we take an independent copy of our original known distribution and we apply the inverse to that. Now, it won't usually be invertible because theta and y won't usually have the same dimension, or theta and u won't have the same dimension. So he introduces essentially an auxiliary function to adjust for the dimension reduction. And the result is a density that's proportional to the model, the likelihood, times something. And the something is called, he calls it a Jacobian. And so it's really looking like a Bayes posterior now. We're taking the likelihood, the distribution of the data for a particular theta, and we're multiplying it by something, and then we're normalizing that, and we're calling that a fiducial density. And in the case of generalized fiducial, there's various versions of this extra factor. D stands for generalized determinant, and this is the theta derivative of the generating equation. So it has very much the flavor of what Fischer did. If we used just an ordinary determinant, so if D was just the bars, like I've had here, then G of U and theta is Y. So this is like dy d theta, and that's the way that Don Fraser developed it, as just a kind of total derivative, the change in the data that goes along with the change in theta, which is a very odd way to think about things if you're not in a location model. And in fact, since they have different dimensions, this determinant doesn't quite make sense. So you need to define it the way we do in regression, as the square root of the determinant of the matrix transpose times itself. But so if we replace the j here by dy d theta, it would be like using dy d theta as a kind of prior for a likelihood function. It's a data-dependent prior, obviously, and it's not a, so what we get out is not a probability because we've put in something that isn't a probability. The strength of the generalized fiducial approach is that it's very well adapted to simulation, just by the way it's set up, and it's applied Jan and his colleagues have applied it in many interesting and complex models, but there are no guarantees on calibration. So if you get out a multivariate fiducial, generalized fiducial density, there's no guarantee that you could marginalize that to any particular parameter. You need to check one by one. Okay, significance function, I'll also skip. It's expanding on this notion that if you, instead of using one of Jan's very clever constructions of a generalized determinant, if you use a simple determinant, then you get the same function out. So I'll maybe skip all that, but just remind you that marginal posteriors are not guaranteed to be calibrated. That is, they're not guaranteed to have, the credible intervals are not guaranteed to have good coverage, but they will agree to first order, to the normal approximation. And fiducial, none of these distributions are guaranteed to be calibrated. This may be a little bit clearer if you're coming at it from an objective Bayes or fiducial or confidence approach, that you do need to think about what parameter you're going to measure before you start. In fact, the confidence method that's developed a lot by Mingei Shi and by Niels Hjort is to choose a particular, often a likelihood ratio statistic, and base all your confidence distribution on that. So decide on your parameter that you're going to target, find something that measures it, and then do everything that I've talked about today. So it's maybe, if you're not using a Bayesian approach, it's maybe a little bit easier to see when you start that you're going to have to think about this more. I just said this, I said it, I think, better here in text, but the confidence distribution approach relies on the user to identify some quantity that measures the parameter of interest. Okay, so now what I said, that we have to think about the nature of probability and in these different but very similar versions. So in a standard Bayesian approach, the probability that we get out is epistemic. It summarizes our understanding of our uncertainty about the parameter, but it's in objective Bayes, we try to make that also an empirical prior. and in the generalized fiducial approach, the usual discussion of it emphasizes that these are meant to give empirically valid confidence intervals or fiducial intervals for parameters. Confidence distributions are a little more complex because one group of people working on them says that they're meant to be epistemic probabilities, and another says they're meant to be empirical probabilities. So I think it's not quite decided yet. So all this to say simply that I don't think the dust has settled. I haven't even talked about inferential models, but I don't think the dust has settled on how we decide between what and how we think about what a probability statement that we're making actually means. Okay, so let's go back to something maybe a little bit simpler, back to the Andromeda trial again. So this is, now I've got the whole table of numbers, which are probably super small, but I just wanted to think about it a little bit more. So here's the credible intervals for the odds ratio. With a prior that favors the new treatment, the upper limit is 0.9. With a prior that's somewhat neutral, but not completely neutral, obviously, the upper limit is 0.96. And with a prior that favors the old treatment, the upper limit is 1.09. So the priors are having quite an effect. I mean, we could still say, okay, these probabilities are all more than 90%, so we should be looking at the new treatment. But the priors are having an impact, and we haven't even thought about the other priors that were on all the covariates. This is maybe more of a worry than all this angels on the head of a pin about the nature of probability. This is supposed to be the prior that corresponds to a frequentist analysis, although strictly speaking, I don't think it does. And it has an upper limit of 0.92. And remember that when they first did the analysis, the upper limit was 1.02. So we've suddenly the frequentist, supposedly frequentist answer is giving us a statistically significant result. But they changed the analysis. They changed from a proportional hazards model to logistic regression. And they added a random effect for centers. So the model changed as well as the priors. And I was a bit surprised that you would get a stronger result with a what might be thought of as a more crude model, because this model is, yes, you survived 28 days, no, you didn't. Cox proportional hazards model measures how long you survived. So you should be using more information in that Cox proportional hazards model. But for some reason, the impact of the new treatment seems to be stronger in this setting than it was in the Cox proportional hazards meeting, the evidence in favor of it. So something funny is going on under the hood, and I don't know what it is. Okay, thank you. So just summarizing this again, the initial analysis was, as I said, not statistically significant. That got translated into the new therapy has no benefit. The second analysis was the posterior probability that the odds ratio is less than 1 is whatever it is. And that got translated into the new therapy is better. So is more study needed? Every paper ends with more study is needed, right? And maybe we need a Twitter poll to find out. I can't quite decide. I rail against people out endlessly writing more study is needed. This was a complicated trial to set up, and they thought carefully about how many people they needed, but they thought that the difference would be bigger than it was. So the frequentist analysis did use some prior information. It just didn't use it in the form of probabilities. They did a power calculation. They said, well, we expect the new treatment to be about this good, and we want to be able to detect that with high probabilities. So they did use some thoughts about the new treatment, but they were overly optimistic in their thoughts, and so they had fewer patients than they needed. So, I don't know. I haven't decided. Okay. Now I'm going to a more free-ranging discussion that's less about these distributions for parameters, but more on how we're going to move the field forward, because there's what we do internally that's all exciting and important, and when we're working with our colleagues, you know, we make a lot of advances on it. But then there's this concern that, you know, sometimes important conclusions turn on a particular adjective being in the concluding sentence, and I don't think that's so good for the profession. So I guess I'd summarize that by saying, well, I think we can all agree dichotomizing conclusions based on p-values is not a good idea. It's much more complicated than that. And science rarely advances on the basis of a single study. I'm actually quite surprised, though, how many scientists I meet. I mean, I don't meet that many, but how often I meet a scientist who views the statistical work as the gatekeeping for their publications, which I think we've all probably come across that, right? And I would have thought that had gone away, but it doesn't seem to be going away very quickly. So we do have to work on that. I would caution that posterior distributions need to be treated with care. And there are several sort of versions of fiducial inference, confidence distributions, significance functions, generalized fiducial distributions. These are all very, very similar, and they're all really trying to avoid using prior distributions, but somehow you need to then look at things in a slightly more complicated way. In applications, we need something that works, right? We want sensible answers, not too sensitive to model assumptions, computable, provides interpretable parameters. Where does foundations have a role to play? Well, I think that the foundations can help us avoid apparent discoveries based on spurious patterns and shed light on the structure of the problem. But probably the most important point is the last one, that they help us to understand when and why methods work and when they fail. So there's got to be an interesting theory, maybe it's already been done and I just don't know about it, that if you change from proportional hazards regression to logistic regression, some things are going to change and be expected to change in a certain way. And that would be of interest not only for the Andromeda study, but for all kinds of medical studies that are being conducted every day. I'm finished. Thank you.
So please use the microphone if you have any questions or comments for Nancy.
Yeah, thanks so much, Nancy, for a wonderful talk, really clarifying lots of things that have seemed mysterious to me anyway. Just a quick question. You've talked about a flavor of Bayesian inference, which is looking at the posterior probability that the odds ratio is less than 1, right, rather than greater than 1. And another form of Bayesian inference for things like odds ratios is looking at something like a Bayes factor, or for basically the null hypothesis versus the alternative hypothesis, which gives somewhat different results. So, and that was due to Jeffries originally, and I was wondering if you had any thoughts about how that approach might fit in comparatively with the approaches you've been looking at.
Well, that's a good question, and I haven't really looked at that because I've been so focused, blinkered on distributions for parameters, and the Bayesian approach to hypothesis testing really gets away from that, and kind of, I could see in model selection that could be very helpful, but in terms of inference for the odds ratio, I would find that probably an uncomfortable way to do the inference, but I'm sure others would disagree. But it would be easy to look at in the context of this example and maybe enlightening. Yes, thank you.
Additional comments?
It's not a question, it's more of a comment. It's for the profession. I, of course, enjoyed your talk. The problem for the Bayesian is teaching, teaching our first year or second year students. So like first we tell them theta is a parameter, it is unknown, but it is fixed. Now you say in Bayesian, oh, we put a distribution on theta. And the students say, oh, so whatever you were telling me before, it was all not correct. And that's a very hard thing to answer. I mean, because then you cannot go and start introducing distribution of parameters and fiducial distributions and so on. Actually, fiducial distribution I found easier to convince because it's based on the observations. That's what you have, and now you invert it, and you get whatever you get. So a way to do things. Now, one sort of way I tell them that, give them example that, well, it's true that we assume theta is unknown, but fixed. But now you, in practice, you have some idea. Like, let's say you say you want to you want to predict height of a group. You know certainly height is between certain and certain bound. So you give some prior. Well, it will be a subjective prior, but probability is one way to introduce this. So I say to save myself, I still say that theta is actually fixed, but of course you don't know. So probability is a way to put your idea into, and it's easy then once you put a probability on your idea, call it prior, then you can easily do all the mathematics. So this is the comment I wanted to make. Maybe you have some experience about this yourself.
Well, everything about teaching statistics is hard, especially at the elementary level, but maybe there's some mileage to be gained in emphasizing the two different notions of probability. One is the long-run frequency that they'd be familiar with from the beginning, and the other is the uncertainty of our knowledge, which is a slightly different form of probability, but both are useful.
So I guess we have another event that's going to be starting in a few minutes. So anything that you need to say?
We have another talk.
Oh, is there? Okay. So sorry. So we'll have to terminate this session, I guess. And if confusion is the true path to enlightenment, I think we've really made big strides today. So I'd like to thank you very much for confusing us.